Um, and it gives me an excuse to talk about, you can't talk about amplification until you talk about what you have before you start amplifying. So there's kind of a historic perspective to this topic. You could argue that we're always amplifying what we do as new needs arise and as the field evolves and as the technologies change. And so it's kind of a natural state in informatics to be expanding and amplifying the basic methods and techniques that we make use of. So I will use the era of genomic medicine to make some of the points, but I want to put this in the context of the field as a whole. One of my goals today is to try to synthesize across biomedical informatics as a discipline. Most of you have not seen much of this before, but a few of you will recognize a few slides and things like that. But they're part of an effort on my part to remind you that there's a very big picture here in this field, and we sometimes end up very focused on our little areas or our little projects, and yet it all fits into a kind of continuum, both historically and also across a very broad spectrum of areas of application. It does make it hard sometimes for us to wrap our minds around the full extent of the discipline, and I'll acknowledge that and tell you a little bit about how I think you can try to get a feel for, as a student, what you really need to understand about the field as a whole, but what you also need to be able to convey to folks that aren't in the field and are trying also to understand much more about what informatics is and ought to be. A lot has happened very quickly. I happen to be just gray enough that I have been around almost from the beginning of the field, and it's been quite a wild ride when I look back, especially because of the explosion in the technology as well as the underlying scientific discipline, right? So if you go back to about 1984, I love to use this slide because it was absolutely the first time I ever saw anything in the general medical literature that suggested doctors and computers might go together. It was an ad for an antihypertensive agent in the New England Journal of Medicine. Okay, it wasn't an ad about computers. You can tell it's pretty old, just look at that computer. In fact, I'm not sure that computer ever actually existed. I have no idea what it was, but it doesn't look like any PC I know. So we went from that, maximizing patient benefits. That's actually a pretty positive portrayal of computers in 1984 with doctors. That's at a time when not too many doctors felt very positive about this whole idea. And by 20 years later, that was in Business Week. The doctor had moved from the user to being actually in the machine somehow, as we began to look at what all this computing in medicine meant, right? So there's been quite a progression, and there's still a lot of uneasiness as well as recognition that it really is a force that cannot be ignored. So when did it start? Some of you have heard me claim that probably if you had to pick a kind of seminal event that started the field that many of you were in, it would be this article back in 1959. It was published in Science by Ledley and Lusted. They were two researchers, one a dentist, one a physician at NIH, and they wrote this article called Reasoning Foundations in Medical Diagnosis. And now that you've been students here for a while, I won't surprise you if I tell you that in fact what this article did was point out that there was a statistical basis for diagnosis and that there was this thing called Bayes' theorem that could be used for doing diagnosis. And also there were computers that could do the calculations for Bayes' theorem, and maybe we should be looking at how computers could help us do medical diagnosis. And it's fun to read that article, which is still widely available because it's been reproduced over and over again in books and the like because of its historic importance. The reason I say it's kind of the starting point is that if you do citation analysis, that means looking backwards from all the current literature to see what they cite and then go to those articles and see what they cite and then go to those articles and see what they cite and so forth, you begin to see dominant influences where the citations just make it really clear that they kind of had an ancestral importance for the field. And in the case of informatics, this article is like the granddaddy article of them all, okay? And we really began to see computers being used quite a bit in biomedicine starting in the 1960s, mostly in hospitals, mostly to manage patient data. So these were clinical systems. There was a first NIH study section looking at grants. The kind of grants people wrote were very applied. They were just trying to figure out what they could do with computers in managing large amounts of patient data. So over time, we began to see a discipline begin to emerge from this early recognition that computing had a lot to offer to that world of healthcare. The word informatics finally came along and was pretty much adopted by the mid-1980s. We started hearing it in the late 70s, but it really became kind of accepted in the 80s. It's borrowed from European languages. Informatique is the word for computer science in French, and people liked informatics because it seemed to emphasize the information and knowledge content of a discipline rather than the computers per se. And I'm getting a little tired of the exploding interest in big data because it seems to me we've always had big data. This is just a current buzzword, one that seems to be attracting dollars from NIH agencies, so it's hard to ignore when that happens. But if you think about it, the reason they started using computers in hospitals in the 1960s was, to them, they had this huge amount of data that they were trying to deal with, and they had to develop the methods that would allow them to actually adapt early database technology for purposes of managing clinical information. And those of us working on decision support and expert systems in the 70s, the complexity of those problems had to do with the incredible amount of data that we felt we were having to sort through and understand. All the clinical research systems that kind of emerged in the 1980s, similar issue. To them, that was big data. And of course, we have the Human Genome Project pushing into biology in the 1990s, where we really were beginning to see even more impressive amounts of data that needed to be managed. And so in each of those decades, big data seemed to be the problem. We just didn't call it big data like that. But today, maybe it's bigger now. I think it is. We'll come back to that. So around about 1985, those of us that were beginning to do training in this field said, you know, it's really hard to teach this field using Xeroxed articles. And of course, there was no online resources for distributing articles in those days, so we were handing out readers of articles from journals. And finally, we decided it was time to actually create a textbook. It took several years. It finally came out in 1990, and it was called Medical Informatics. That term by 1990 was pretty well accepted. And then it was Computer Applications in Healthcare. Okay? And I'm going to use this book to illustrate how the field is evolving, because each edition we face new challenges in making changes to the book, adding new topics, pulling out some old ones. And so just worrying about a book like this forces you to think broadly about a field like this one, because the book is intended to be the introductory course. And I think you guys use it in your intro course here too, right? Not this version, I hope. So we divided the book from the beginning into the methods and the applications. And it's interesting, I don't think we were as aware of that importance of that distinction right in the early days, but the first part of the book is about methods, and these were the only, kind of method-oriented chapters in the first edition. Medical decision-making and the methodology of that. Something about computing, data systems, how data are managed, and essentials of computing and system design. There was a chapter on evaluation, and that was kind of it for methods. And then there was a lot about applications, and they're all very clinical, right? Medical record systems, hospital information systems, which was still the way we referred to these systems back then, lab systems, pharmacy systems, radiology systems, clinical research systems, health assessment systems. The health assessment was the old multiphasic health testing, when you actually put people through kind of assembly line of history taking and physical examination done by machines as well as by some clinicians. And out the other end, you came with a very full assessment of how you'd done. Okay. So throughout, we've had to deal with the fact that we didn't know what to call the field. Probably the first thing people called it was simply medical computer science. We had a group at Stanford when I was there called the Medical Computer Science Group. It basically did what you all do here, but that was the name we had for it. Somehow or another, it bothered people, though, including those who were using that name, because it focused on the technology, when we all felt that what we were really doing was dealing with something much more fundamental in the way of information and knowledge processing and use and good decision making, and that's really what the core of the field was. Now, some people say, well, we would better get information emphasized then, so let's call it medical information sciences. And when we started the training program at Stanford, that was actually the name of the degree for many years. But it has this problem that it's associated with libraries and library science and the like, and people got the wrong impression about what the field was about with that name, too. And that's why we ended up, by 1990, with a textbook that was called Medical Informatics. But of course, things didn't stop there. During the 1990s, a couple of things happened. One was there were subgroups of people in the community that didn't like the word medical. Okay. In particular, it seemed to leave out non-physician health professionals. And second, it seemed to de-emphasize health promotion and public health as opposed to seeming to be too focused on disease. So there were those who started to call the field health informatics instead of medical informatics. Then the other thing that happened in the 1990s, of course, was the Human Genome Project and the explosion in biology. And by the end of the decade, it was clear that you could not do life science research without computers anymore. And in the 80s and 70s, there was lots going on that didn't involve computing at all. And that's been a hard transition for people who were wet bench scientists, starting to produce huge amounts of data with the new techniques that emerged during the Human Genome Project, and not having the skill set necessary. So suddenly they were looking for postdocs and PhD students from informatics programs to come work in their labs and help them actually get their arms around the data. Right? So you will have then seen the move to the word biomedical informatics. I'm going to talk a little bit more about it in a second, but basically it was an attempt to say we have to acknowledge that there's this broad spectrum, and it isn't just clinical anymore. There's this important biological component to the field. And recently, I've even heard a fair number of people refer to the entire discipline as bioinformatics. Wrong, okay? So when you hear people say, oh, you're doing bioinformatics and you're working on an app to be used in the clinical setting by physicians, that's not bioinformatics, is it? Okay, do we all agree on that? But I can tell you at ASU, I have run into lots of people that refer to this department as bioinformatics. They don't have it straight what the difference is, and I'm going to talk about that. Now, there was a field that emerged during the 1990s called bioinformatics. These are both from early in the new century, journals, books, and the like. There's no question that informatics methods were being used in the life sciences, and they called it bioinformatics. But part of the promise of all this, in fact, the motivation for what was going on in the Human Genome Project, if you think about it, was we have to start to understand how the genetics of individuals affects the way in which we're going to diagnose disease, choose treatments, and basically personalize the way in which they're cared for. So there were tremendous potential synergies between what goes on in the genetic, genomic, proteomic world and what goes on in the clinical world. We saw that the same methods and techniques had broad applicability. Certainly, if we have a problem with terminology in the world of clinical medicine, we also have a problem with terminology in the world of genomics and genetics. And the interdependencies seemed very clear. In fact, everybody was working towards creating interdependencies. And yet, as the academic groups and the training programs began to evolve, we saw this schism that occurred between the folks who were doing bioinformatics and the folks that were doing so-called medical informatics. Okay? Now, it's true that many of the people doing bioinformatics were fundamentally biologists who were motivated by the biological problem primarily. And they'd grown up in a life science environment, maybe not even in a medical school, maybe not even with patients in mind, but were working more on the basic science end of the spectrum and not even that related to the health science campus of their university. Whereas the medical informatics folks were essentially all in medical schools or nursing schools. And nurses, by the way, didn't like calling it medical informatics either, so they tended to use health informatics for the field. So in an effort to hold the field together, to keep these centripetal forces from allowing it to kind of break up, there was an effort to rename the field by the early part of this century as biomedical informatics, to bridge it. And departments like this one have explicitly tried to make sure that you both are taught about the full spectrum and also that there are faculty that have expertise across that spectrum, all doing informatics, but doing it in different areas of application. So this is the part that some of you will have seen, but not all. Think about this field. And by the way, this has become, you heard I was at AMIA, and I fortunately got this, I did get it instilled in the AMIA mindset while I was there. And so this is the way that AMIA, the American Medical Informatics Association, which of course should be the American Biomedical Informatics Association, right? But it was named in 1988, so it's got that history behind it. This is the way they agree we should think about the field, and this is the terminology that they're using. Okay, that there is a basic science discipline, and that's typically what we name departments after, is the discipline, right? And that's biomedical informatics, and it's a set of methods and techniques and theories, and they grow over time, and you learn new ones and create new ones in response to the growing needs of the application areas in which you work. But there's a whole lot of effort, which we might call applied research and increasingly practice of the discipline. Okay? And as I've indicated, the clinical world is where most of that started, clinical informatics. But very soon after it got started in the 1960s, we saw more and more use of informatics methods in dealing with images. And radiology departments became very computer-oriented and high-tech compared to the rest of the health science environment, as did pathology departments quite early. Pathology often involved with imaging as well. We saw bioinformatics emerge for the biology applications, life science applications during the 90s. And in the last decade is when you've really seen the exploding recognition of public health and public health informatics as another area of application. Okay? So by this diagram, bioinformatics is one of the many application areas of the field of biomedical informatics. And clinical informatics is meant to contain within it nursing informatics, dental informatics. And today, medical informatics is being used pretty much to refer to disease-oriented, physician-oriented informatics activities, okay? So we don't call the field medical informatics anymore. If we talk about medical informatics, as some hospitals do, they're pretty much talking about doctors and disease, and certainly not public health and the like, okay? Okay, so we all agree these are not the same thing, eh? And you now have an explanation you can give to people who use bioinformatics inappropriately to refer to the field. All right. So it's a broad field, much broader than many, very interdisciplinary. Can't work in it unless you're collaborating. I don't think I've ever seen a really good one-person informatics project. Doesn't make much sense, does it? Even dissertations. So molecular and cellular processes, the imagers more at the level of tissues and organ systems. So there's obviously radiology, but pathology, hematology, dermatology, visually oriented fields. And we have Jimmy working in that area. Clinical informatics, the entire patient. Public health informatics, populations and society. Right? Okay, now, lest we pretend there's no such thing as health informatics, everybody I know who wants to call the field health informatics is working in applied clinical or public health informatics. Okay. or they're either researchers or practitioners in that area. They do global health. They want to call it health informatics. So AMIA and others have agreed health informatics is essentially those two boxes. If you had a department of health informatics, you would not get any bioinformatics faculty to join your department. They would feel that this was about the other end of the spectrum here. Right? Okay, so these are also not synonyms. All right, so we did have a second edition of the textbook come out in 2000. Still called it Medical Informatics, but you'll notice that the subtitle was now not Computer Applications in Healthcare, but it was Computer Applications in Healthcare and Biomedicine, because it was pretty clear that things were changing. By the way, in 1990, not one mention of the internet in the book. 2000, every chapter. Okay? That's how much things changed in one decade. So in the second edition of the textbook, the new things I've underlined on these slides were new, not in the previous version, and an indication of the evolving understanding of the field. So the methods had started to get beefed up. We'd added standards as an important issue because of all the integration and interoperability concerns, ethics, legal issues, technology assessment. So new chapters in those areas. And on the case of applications, things really started to change. Instead of medical record systems, we talked about computer-based patient record systems. Those of you who know the early reports that introduced the concept at the Institute of Medicine may remember that the medical record systems were called computer-based patient record systems, CPRs. Okay. Public health chapter, consumers, information systems and integrated delivery networks. Patient care systems, that used to be called nursing informatics. It's written by nurses, but they didn't want to make nursing the point of the articles. It was about patient care, that chapter. Imaging systems, new. Information retrieval systems, Medline search and all the things that followed. And the last chapter, a chapter introduced on bioinformatics. This was in 2000. So it was written in 98, 99, okay, at the end of the Human Genome Project efforts. Now recently, Jamie has published this AMIA statement of the definition and the core competencies in the field. Since many of you are being trained in the field, this might be a good time for you to look in this article if you haven't and see if you think the core competencies you're requiring are a good match with what is described in the article. Okay, but this was an effort by a group of people working with and then finally approved by the board to define what ought to be in a graduate education program. It's not for certificate programs, it's not for 10 by 10 programs. This is what you should be learning if you're going to be a master's or PhD in this field. And this is the definition. An interdisciplinary field. By the way, every word in this was selected with great care. It took like 3 days to develop this definition. Interdisciplinary field that studies and pursues the effective uses of biomedical data, information, and knowledge for scientific inquiry, for problem solving, for decision making, always motivated by efforts to improve human health. And the emphasis on human health means that the interests of biomedical informatics in the bioinformatics area tend to be more on so-called translational bioinformatics. You know, there's not a lot about fruit flies going on in this field, except to the extent that fruit flies allow you to develop methods that are important for human disease. Okay. Now there are 4 major sub-themes that they also identified in this article. Corollaries, if you will, to this definition. First one is that there really are theories and methods and processes in this field. The notion that biomedical informatics people carry wires through the halls, string them in the ceiling, and make sure you have Cat5 in every office, wrong. Okay, that's not what this field's about. I think everyone in this room knows that. But a lot of people do not understand the difference between health information technology and computing support and the discipline that this department is based upon, and I trust all of you are learning. It does have, although it's not in that definition I gave you, but it does have an inherent connection to computing and communications. It'd be pretty hard to do data, information, and knowledge in the modern era without some deep connection to computer science, right? Third, that it's really broad, from molecules to populations, with a variety of biological systems, bridging basic and clinical research and practice, and the entire healthcare enterprise, including disease prevention and health promotion. And finally, this is a human-oriented science. The users are humans too, and that means that unlike some pure computing science programs, you have got to learn a lot about social sciences, behavioral sciences. That's the reason that we see cognitive science increasingly in these departments. And healthcare financing and the issues of privacy and security from a, obviously there's a technical side to security, but there's also a human side to security and the trade-offs and the like. So social, educational, financial, organizational theory, these are all workflow analysis. These are increasingly viewed as key parts of the field. All right, well, I gave you a kind of simplistic diagram, and the world has to acknowledge that there are no sharp boundaries among these areas, right? And many of you may feel, in fact, that you're working at something which crosses these boundaries. It's pretty easy to think of examples. Biomolecular imaging, for example, which is increasingly a big part in radiology departments, is clearly got elements of bioinformatics and imaging informatics in it. Consider the whole burgeoning area of pharmacogenomics, which clearly requires looking at both genomic and phenotypic data on the same patients and bridges clinical informatics and bioinformatics. Highly translational science in its orientation, right? Consumer health has got elements of patient care. It's also got elements of population health and prevention and the like. So it's kind of at a boundary between some of these areas as well. And you could, I'm sure, think of other examples. In fact, I'm going to give you another one later. Well, what about the education? Well, you look at that diagram, and if you're a student in this program, ask yourself, what have I learned about the various things in this diagram? And I would hope that you've been exposed to things both at the methodology level and at the applied research level, okay? And that you, even if you're working in clinical informatics, that you've had some exposure to bioinformatics and vice versa. But you're all doing projects, you're doing research, and research in this field requires informatics innovation, okay? Certainly if you're going to get a PhD. I would argue most masters can also be quite innovative at that level, right? So, if you're working on apps, that's the bottom of the diagram. So ask yourself on every app, what am I doing that's a contribution to informatics? The app itself probably isn't. But think about what you had to do different in order to make that app work, and you'll begin to tease out where your informatics contributions are, and what I hope you'll make a point of writing about. That's how you advance the science. All right, so this third edition of the textbook came out in 2006. You notice the name had changed to Biomedical Informatics. Still computer applications in healthcare and biomedicine. Of course, it had gone from 600 pages in 1990 to about 1,200 pages, and it like doubled in size. And I can't imagine what this next one's going to be. I'll come into that later. And the methods that were emphasized in this one, new methods: cognitive science, natural language, and text processing. In retrospect, how did we ever not have them in there in the first place? You know, they're pretty crucial areas. But our understanding of what needed to be included evolved over time. And now it's not computer-based patient record systems anymore. It's electronic health records, and there's public health informatics and the NHII, the National Health Information Infrastructure, consumer health, telehealth, bioinformatics still there. Okay. Now, so that in a sense is what we're at, where we are right now. And this is where we need to talk about amplification in the era of genomic medicine. Right? Our goal has always been, and this diagram would have been just as apt when I started working on my first EHR in 1968, as it is today. This notion that there are providers caring for patients and that they need to be recording their data so that the data are handled in a much more apt way. And you've all heard the stories about why paper-based records are a mismatch with the modern era and have been for 30 or 40 years, really. Now, you could argue that that's all you need to draw, and you've got an important contribution. People using electronic records, putting data in, being able to get them out, getting test results out, making better decisions because they have better access to the data that they can't get well from patient records. They can communicate using it with other providers. And indeed, that's a really important reason for putting in EHRs. But if that's all you do with your EHR, the Office of the National Coordinator says you are not making meaningful use of your EHR, right? At least not enough. So everybody's heard the meaningful use phrase, and they basically says there's more. All those data that are being collected in electronic health records are potentially useful for biomedical and clinical research. And we need to get them in a more facile fashion into the kind of databases, either regional or national, or increasingly even international, the disease registries that inform us about what's going on. There's this notion that the medical record has locked up for too long what we know from what we do. And anybody who's ever done a medical research project with paper charts, sitting on a desk, looking through them, trying to fill out data sheets, all that kind of stuff, knows that can't be the best way in the modern era to do this kind of thing. We can extract evolving standards over time for prevention, treatment, management in general. And those can lead into the creation of protocols, guidelines, educational materials, the kind of things that kind of summarize what we've learned from our experience, which then feeds back into information systems, decision support systems, reminders and order entry systems and the like, and actually has an impact on the way in which providers care for patients. Now, this cycle, which we once knew we wanted to accomplish but had no idea how to do, in an era of networking, standards development, system integration, HIEs, health record banks, and the like, we're beginning to see how this might actually happen, right? Now, this has been called a learning healthcare system, a system that actually learns from what it's doing. It's not randomized controlled trials, although it can also feed into RCTs. But there's so much that we can learn through careful data analytics of big data. And these are big data by the time you do it across large populations. Right? That, especially in those areas where RCTs are either too expensive or take too long or the like, there's knowledge to be gleaned. We could do better. Institute of Medicine's had a whole series of reports and workshops on a learning healthcare system. This diagram, I don't know if the diagram's been used in them, but it's the notion that they're increasingly identifying as being key for the future. Now, in the midst of all that, we're seeing this exploding interest in actually beginning to use all that genomic information. Peggy Hamburg there, the head of the FDA, Personalized Medicine Coalition, lots of websites. You go out there and you start looking around and you'll find a tremendous amount of information about personalized medicine. Some of it is generic, of these like the ones I just showed you here, but then you start finding universities have got websites. This is University of Utah and their efforts. They have huge genetic databases that they can use for these purposes in Utah because of the way in which data have been collected through the Mormon Church for years. Stanford. By the way, I just picked a few. There are many, many of these out there. And then I picked Mayo because they, and they're not alone, have chosen not to call it personalized medicine, but individualized medicine. There's also precision medicine out there. These are all basically the same notion. So let's come back to this diagram and think about the implications of that kind of combining of genetic information with the rest of what we know about a patient in order to make good decisions about their care. And you'll begin to see lots of new little research challenges. Remember, things that you order on your patient or that other physicians or other practitioners have ordered on your patients go into data systems. The orders go into the data system. The data are collected, and they are eventually stored in the EHR. And you access that EHR when you're making decisions about your patient. That's the data you want to see in order to make decisions. And maybe we'll even add some decision support so that you can get help figuring out how to care for those patients. But we are now talking about a whole new kind of data to go into those data systems and then from them into the EHR. Data of a type that's markedly different from getting a complete blood count or a chemistry or even an X-ray report. Okay? Because of what's happening in the world of genomic medicine, the research world out there, we have to rethink what goes on in electronic health records, what we store, which parts of what we know we capture today, what parts should be left out and left for the future. What do we do with primary as opposed to interpreted data? I'll come back to it. It affects the way in which we're going to need to give decision support. You know, clinicians know they don't know this stuff. This is getting a little complicated. And most physicians have not been trained in genetic medicine. And there's new results coming out all the time. You don't know whether or not the cost-benefits trade-offs are reasonable. And so the notion that you would get some help deciding what to order and how to interpret it is increasingly being accepted in this area. And much of that would be blended into the order entry environment, right? So the order entry systems have to reflect this new kind of knowledge. The registries are going to start storing different kinds of information. There are new questions about standards. And the kinds of guidelines and protocols, decision support fodder that you produce from this process get more complicated as well, right? So, as we push to move from the bottom to the top of this diagram, the digitized EHR from these old paper charts, you can look back on what we're in the midst of right now. Pretty remarkable change over the last decade. It's about almost a decade now since President Bush announced in his State of the Union address, he actually used the phrase electronic health records. For people who've been working in the area for 30 or 40 years, to hear the president actually utter those words was remarkable. Okay. Now, he said everybody was going to have one in 10 years. That's next year. I wouldn't hold your breath for that to happen in 10 years. I don't believe President Bush had any idea what would be involved in trying to get a chicken in every pot, an EHR in every doctor's office, etc. But the concept kind of got popularized. And he mentioned it every year in his speeches, as did Tommy Thompson, who was the secretary of HHS, and his successor. And by the time we went to the 2008 elections, it was pretty clear that there was bipartisan support for this idea. Certainly, Obama was all over this issue as a candidate, which is when I got this picture back before his hair turned gray. And so, the vertical line you see there is the passage of the Recovery Act in February, March 2009. And what this diagram shows you, it's probably a little hard to read from the diagram itself, but this is the rate of increase of jobs since the Recovery Act was put in place. And as you know, the job market has not done all that great. So purple line is the growth rate for all jobs in the U.S. economy. This is through the end of last year. Health jobs are in green. Health IT jobs are in red. So I showed this to Keith Lindor, and he says, yeah, well, maybe there really are jobs out there for the graduates of these programs. The demand is definitely up. Okay? And there's a belief that, although it won't happen in 2014, that the penetration of EHRs is going to be extremely high over the next 5 years. The penalties start kicking in a few years for those who have not implemented them. Okay. So those who are recognizing these issues, here's an article that was published by folks who held a workshop at the NIH on the integration of genetic test results into electronic medical records, recognizing there are a lot of questions about how to do this. And I'll give you an example of the kind of things people are thinking about here. They had 7 major desiderata that they defined. We have to somehow or another separate the primary molecular data that we generate by actually doing genomic testing from the clinical interpretations of those data, because we know that the interpretations are going to change. So if you store it in there just as the interpretation, you can't go back and relook. You have to support lossless data compression from primary molecular observations to the clinically manageable subsets. I think everybody knows what that means. And the notion is you need all the data. You can compress them, but you can't lose any. You have to maintain the linkage of the observations to the lab methods that were used to generate them, because the lab methods are changing. And your ability to trust or believe or interpret may very much be affected in the future by how you know that data in the chart were gathered in the past, or measured in the past. You have to support a compact representation of clinically actionable subsets for optimal performance. So the stuff that we do think is clinically actionable now better be in a form in the chart that allows you to quickly generate the kind of decision support that's necessary, even though you're attending to those other issues at the same time. And you have to make sure these are human viewable. Yeah, I mean, there's got to be some human being's ability to have faith in them, to understand the interpretation, to know why they're getting the advice they are. We have to understand that in the future there will be more fundamental changes in our understanding of human molecular variation, and that has to be kind of anticipated in the design. And we have to recognize we're doing this not just for the care of patients, but also for future discovery science, future research, right? So we have seen some big changes in the last decade or so as the computing technology that was kind of in its infancy for so long finally began to really take off in healthcare environments. So there are enough people here who are physicians who have been around a while that you can remember when this was the picture. You know, you got a piece of X-ray film and you held it up to the light and put it up on a screen box, and that's how you looked at X-rays. And that is pretty rare now. We're in an era now where almost everything is digitized, and those big folders of films are starting to go away. And we're now seeing new kind of viewing modalities and capabilities that are changing the way in which people practice. And I use radiologists here because they've tended to be the quickest to adopt the technology among all the specialties. So the question going forward, of course, is, yes, we're still going to have doctors taking care of patients and doing bedside care, but are they going to, in fact, be looking not only at their traditional lab results, but also at their genetic test results, trying to figure out how to take that into account in the way in which they select drugs or advise them regarding prognosis and the like? All these kinds of information are going to require new decision support functionalities, and there is a big opportunity for new research for people that are interested in decision support in the world of genetics and genomics. There are also big challenges for the privacy advocates. in this world. It's been recognized for the last decade or so. Do you want your genetic information out there? There are people that have had their genetic testing done for research purposes but don't want to actually look at the results themselves. Thank you very much. I don't want to know what my risks are for various things. Of course, the challenge compared to our traditional concerns about data privacy or data confidentiality, patient privacy, is that we're worried about not about what's true now, that you saw a shrink or that you've got an HIV positive blood test, but what might happen in the future, maybe not even to you, but to your children. That's the privacy issue that now is, and it clearly affects the systems, the way in which you share data, what it means to do anonymization of data sets. All right, so let's acknowledge that there is a big exploding interest in big data, and medicine is often used as one of the prime examples, especially the genetic end, because the numbers there are truly remarkable. So what do we mean? Well, a lot of people have written about it. I've been reading several things. This is an interesting report that tries to do some definitions. IBM published it. And they said, in short, the term big data applies to information that can't be processed or analyzed using traditional processes or tools, which kind of invites the question, how do you define traditional? Because traditional changes all the time. Right? So for a little more clarity, there are three characteristics that define big data: volume, variety, and velocity. And that these are all taking off tremendously, and that's the reason we are now identifying this as a new kind of problem. But I would say volume, variety, and potentially velocity were always issues that have been challenging at each era, as I described earlier. Rather than confining the idea of velocity to the growth rates associated with your data, we suggest you apply the definition to data in motion. It's actually the speed at which they move around now in this world, not just the rate at which they accumulate, that is referred to by velocity. And for those of you who don't know what Hadoop is, because I sure didn't, that's what it is, but it's the IBM solution. And I have nothing to do with IBM. This just happened to be a useful source. But since I showed you a slide that has Hadoop on it, I'm telling you what it is. How many of you knew what Hadoop was already? There are a few. All right. I'm impressed. This is a week old, 2 weeks old, right? I mean, this is really getting to be a big topic, and now we've got a request for information about how to do training in response to the need to take these big data and derive new knowledge from the kinds of data that are exploding in the healthcare environment. So that's an NIH initiative. All right, I said I'd talk about the 4th edition of the textbook. This is what I've been working on for the last few years. There are changes. You can go to my website to see this if you want, but I won't go down all the changes. I want to emphasize these ones at the bottom: translational bioinformatics, new chapter, and clinical research informatics, another new chapter. Okay, there are a few other new chapters as well. There's a chapter on health policy and IT, which is probably overdue. It's certainly a big topic in the last decade. All right, so there's still the bioinformatics chapter. So there's bioinformatics and there's translational bioinformatics. So why is this suddenly taken off? The Clinical Translational Science Awards that the NIH introduced about 7, 8 years ago now have transformed the ways in which medical schools and others are thinking about the role of informatics. They required informatics if you wanted to get one of these grants. These grants are big money. There's a kind of club you're in if your school has one of these awards. There was an effort by the University of Arizona with a couple of rounds to get them, but it was collaborative and it included this department in those proposals. Pretty hard to do a statewide CTSA, and I think that experiment just looked a little too risky to NIH. So we don't have a CTSA in the state of Arizona, but Mayo does, at least based in Rochester. And these have had a big impact on the recognition that biomedical informatics is here to stay. It's a crucial part of the core competencies of a clinical translational science organization within a medical research environment. And it's not just to support clinical research. This is an interesting article that argues that, in fact, you need to be able to look at some of the human health databases in order to do good basic research with mice and the like. Okay, so these are human disease data resources that complement the research activities of those working in these basic biological problems. So to go back to my earlier diagram, translational science is actually across the entire bottom of the diagram. It goes into public health, community-based research, imaging, and basic biology. And there's a meeting AMIA does. Some of you know about this one. It's in 2 weeks, but it's been every year for several years. It's called the Joint Summits on Translational Science. It's an informatics meeting. It's 3 days of each topic, translational bioinformatics, 3 days of clinical research informatics. They overlap 1 day in the middle because there's a fuzzy boundary, and that 1 day everybody is there for. Some people stay all 5 days anyway, but the point is there's this continuum as we move from the more basic bioinformatics components aimed towards human disease, its prognosis, its diagnosis, its management. Pharmacogenomics obviously is part of this field. And then clinical research informatics is when you begin to get into things that support the clinical research endeavor, clinical database management systems, and eventually those that take you out into the community. Now, some of you may have seen this diagram that I've borrowed from Bob, edited a little bit, Bob Greenis that is. But it's this cycle of community feeding back into our kind of prioritization of the projects we want to, where we need new knowledge and new understanding of disease, leading to the identification of promising opportunities and then their eventual application in specific projects, and taking those into the clinical setting for validation, and that's called T1 translation, translation number 1, bench to bedside research. T2 and T3 translation have to do with moving it out into the community and then making it standard and accepted. Okay? This is what the CTSAs are supporting. And the NIH in its wisdom, and I think Elias Zerhunia was the director of NIH earlier during the Bush years, gets a lot of credit for that, recognized that you need to have informatics to do literally any element in that. That it's all over our ability to do modern science, and therefore needs to be part of any active program. And that's how you achieve personalized medicine, is in the context of that kind of cycle and the role of informatics. So I'm going to close just by pointing out that there was a report in 2009 from the National Academies on basically trying to inspire computer scientists to find great projects that they could work on as computer scientists in the world of medicine. And there were many examples. I've emphasized the first that they emphasized in their report, which was we need much more patient-centered cognitive support. We need to do cognitive science in the context of these systems. They did a lot of site visits. A lot of the people on the committee were computer scientists, but there were many informatics people and physicians as well. And of course, down here, data management at scale. It's part of the big data story. So I showed you this diagram many times, the notion of the methods at the top of the diagram, the applications at the bottom. All of us in this field are interested in some aspect of applied informatics. We're trying to solve problems that we see in the clinical or biomedical domain that interests us. And when we find those problems, they inspire us to work on a solution. And occasionally the solution is really simple. It's a good applied research project, okay? But often there is no easy solution. It's a complex world out there in biomedicine, and you often have to go back to the drawing board, the top of this diagram, and innovate. And when you innovate, you draw on whatever component science you feel has a potential solution to the problem you've identified. And sometimes it's computer science. And so we learn about computer science as biomedical informatics students, faculty, and the like, researchers. And occasionally the solution that you come up with solves a great problem at the bottom of this diagram, but it's also great computer science. And you publish it in a computer science journal. You make a contribution to computer science. So you can do that as a biomedical informatics researcher if you're well trained in computer science and you understand computing and you recognize the generalizability of the solution that you've come up with. Okay. But not all the problems are computer science. And that's why we don't want to call this field medical computer science, because it's medical lots of things. It's biomedical lots of things, right? It's the decision sciences, statistics, decision analysis, cognitive science, obviously. We talk about that a lot. Information sciences more generically, management sciences. A lot of students want to take courses in business schools when they study this field. Not just to start a company, lots of reasons. Management's one. And other component sciences, organizational theory I mentioned earlier. Okay. So we need more people. A few programs like this scattered around the country aren't producing enough. We need clinicians to know more about it, so trying to get this into the medical and nursing curricula. We need informatics people who really can function effectively as scholarly collaborators with clinicians and life scientists. That means you've got to be part of the culture of healthcare and biomedicine, which is why computer scientists who haven't had the exposure to biomedical informatics sometimes find it difficult working in hospitals or biomedical settings. They haven't got that acculturation to the field. They may come up with very clever computing solutions that are insensitive to the realities of the way in which practice occurs. We need to recognize there's this integrative role of informatics. It touches all areas of biomedicine. There's a large workforce requirement that I suggested on that one diagram as you look at the need for people out there as we implement all these electronic health record and HIT systems. There are implications for the education of people in this field, and that is you need a broad exposure to the content areas and the informatics applications work across the entire biomedical field, even if you are personally focusing in one area. And as I've suggested, you should always be asking how you can demonstrate broad applicability of a solution that you've developed in your own work. What other problem would it be good for? Think about its range of applicability. That's how you make a contribution beyond the specific project that you worked on. And as I've suggested, as a field grows, as this one has, it tends to splinter. And if you have the big picture perspective, you can try to wrap your arms around it and keep that from happening. And departments that cover the entire range are clearly, explicitly trying to do that, to keep those synergies in place, because there are synergies. You can avoid reinventing things that one community is doing and the other one doesn't know about. And my favorite example of that is the gene ontology, which was developed without any understanding of all that we knew about clinical terminology development and the problems that we encountered, many of which were rediscovered in the bio area. And you can re-emphasize that you really are working on shared goals and motivations. And you can design your departments so that they are inherently about partnerships and about coherence across a discipline and identification of those methods, and service to the field, but at the same time being innovative and trying to make sure the field has the ultimate impact. So those are comments I wanted to make. I've run over 5 minutes, but I will be happy to answer questions. Thank you.
All right, questions for Dr. Shortliffe? You can probably just speak.
Hi, so my name is Valentin Dino, assistant professor in the department, and I have a question regarding the integration, potential challenges in integrating genomic and clinical data. And I'll start by saying that I teach a translational bioinformatics class here at the ASU in the spring, and just a few weeks ago we were just doing a demo of 23andMe website that stores genetic information. And it was interesting to see what 23andMe could see about me just from a sample of saliva, that I have blue eyes, curly dark hair, hopefully still dark. But and also, for example, some interesting pharmacogenomic information. I would be a regular responder to warfarin. And a student asked...
Had you sent in saliva
yeah,
swabs?
Exactly.
Oh, I see. So you had your own data on 23.
Exactly. So it's
okay.
all about my information.
Yep.
So a student asked, how about integrating all this nice, interesting data? And they give a lot of information about many diseases. And what would it take to integrate this data with your EHR, with your clinician, with your doctor? And actually, one of the student who asked this question is still here. And I don't think I had a very good answer to her, and I would be very interested to see what you think is your opinion on this, integrating genomic data or clinical data challenges.
So, I mean, the Dan Macy's article that I showed you was about the technical challenges and issues in doing that, but that was based on the assumption that you would, in fact, have the genetic data for more and more patients. And in fact, genetic testing being done as part of your medical care, rather than because you did your own swab and sent it in the mail to 23andMe, is likely to start raising the issues that Dan Macy's and his crew wrote about in that article. When you start talking about what happens when patients are starting to collect data on themselves from various sources, you could argue, is that really any different from collecting data about yourselves from multiple providers? I mean, that's in a sense what we've all done if we've changed physicians or moved or all those things. So this notion that maybe patients, or at least those who are capable of it, and not all patients are, but that patients need to be much more in charge of the gathering, combining, managing, providing access to their own data, that suggests some kind of central mechanism by which they can do it. It's not Microsoft Health fault or Google Health. Well, it's definitely not Google Health. But I'm increasingly a believer in the notion of patient-controlled health record banks that centralize data. There was an early effort to get one started in Arizona. It didn't go anywhere, I know, but I think the politics has not been obviously optimal. But we may well see there are ways that those kinds of problems can be attacked. The technical issues are identical with the ones that Dan Macy's raised. It's just that suddenly you're now talking about what happens when it's the patient in some more regional resource that is the place that's trying to decide what to do with all your genetic data from 23andMe, rather than because it was ordered in an institution where you're being cared for. Watch JAMA next week. You'll see an article on this that I and a couple of other people wrote.
Along those lines, Valentine, I'm wondering that, when you think about integrating this genomic data, you think about, well, I go get myself sequenced and I've got a terabyte of genomic data that it somehow gets associated with my electronic health record. But I can foresee a point in the future where physicians don't make their diagnoses based on signs and symptoms. They make it based on the translational, your transcriptome at that point in time. What genes are you expressing and how much? And if on multiple visits you start acquiring these huge chunks of data based on your transcriptome at that point in time, that could just far outweigh your one-time, here's my genome.
Your one-time genome. Well, I didn't mention it, but the Macy's article talks about how you may need your genome for specific cell lines increasingly too, especially patients with cancer, because the whole point is that their cancer cells have a different genetic makeup or at least as expressed than the normal cells do. So the simplistic notion is, well, they're all just another lab test. It's just that they're huge data sets. Now, some people would respond, I know computer scientists respond and say, look, storage is getting so cheap. And it's true. I mean, when you start getting, USB drives that are terabyte, you begin to believe that this really is getting to be an incredibly cheap commodity. But it's clearly the data analytics of all those data, so that you can do realistic things when you're actually seeing a patient, that becomes the challenge. How do you extract? And it was in those 7 points that were made in the Mesis article. You know, how do you extract from the transcriptome on a given visit the information that you need in order to make reasonable decisions? And who knows? I mean, I don't think I said it here today, but I've often compared where we are today to roughly commercial aviation in 1930. Now, there was commercial aviation in 1930. People were getting on airplanes and flying around the country, and there were even transatlantic flights. And it was a lot better than the Wright brothers, right? But we all know, in retrospect, that that was pretty palsied compared to modern air travel, the technology and its penetration and its use and all that. And I think that analogy with medical records today is quite apt. I mean, we know we're nowhere near where we're going to be with medical records in the future, but it doesn't mean we shouldn't be using them. There are too many good reasons for being part of the process that in fact allows them to evolve properly. But questions like that, we are so far away from doing per visit transcriptome analyses and incorporation into decision support. But I wouldn't be surprised if it happens someday. We don't know how to do it yet.
So this kind of thing raises a number of questions that one would be raised because of it. And one of the things I remember well from Dan Mace's article and others is that we are currently having problem even extracting clinical data for patient use, which are not stored in a way that's easily retrievable. They're not in relational form in any form. Now you've got this new data thrown in. That's going to give additional challenge for storing that kind of data in a form that not only could be extended but combined in any way or even use itself. So the whole area of storing data in a form that is easily retrievable and usable would be a huge challenge. The way it's represented would be another challenge we'll be dealing with in the future moving forward, you know?
Well, a lot of the vendors would argue that they're storing data in a way that's nicely retrievable as long as you practice in the institution that has that system there. Okay. Heaven help you if the patient's seen across town, unless you happen to be in Indianapolis where they actually have HIE working, et cetera. You know, so we're still evolving, I admit, but within a closed environment, we're pretty good now at allowing access to patient data. You really can ask a patient record, something you could never do with a paper record, which was, has this patient ever had a Pneumovax vaccine? And those 3-volume charts, you did not want to have to answer that question with the paper chart. There was no way you were going to spend the time necessary to read all 3 volumes trying to find out if they ever had a Pneumovax, so you'd order another one. So waste. And now it's easy to ask a question like that in most EHRs, right? So that's why I say we're a lot better off, but it's still 1930s vintage, okay? And certainly all the HIE, the health information exchange issues, are far from being dealt with, and we don't know how to do the genetic part in a way that it can be retrieved in a way that's really useful.
All right, any additional questions? All right, thank you again to Dr. Shortliffe.